who's going to be doing the presentation. Enrique, come to the call.
There, can you hear me now?
Yes.
Okay, sorry. So hello, my name is Enrique Acuña. I work for CanmetMINING, and I'm going to present today about mining complex waste heat recovery. This is a joint presentation that was developed between Jan Germain and myself. And this is hosted by the Center for Excellence in Mining Innovation, CEMI. Okay. And there. Yeah. So the presentation has 6 different portions to it: an introduction to what is waste heat recovery. Then we'll jump to where are the sources and where are the loads, so you can do the transfers from one to the other. Then we'll look at what are the potentials of heat recovery at mine sites, and the energy transfer modeling, which is a piece where CanmetMINING is going to be of help in the near future. And finally, some conclusions. So first, what is waste heat recovery? So if you read straight the definition, it's basically reutilizing the waste heat from a source, which would otherwise been dumped into the environment, and to reuse it in a load, so you can reduce energy consumption. So basically what you do is you recover waste heat from one side and you bring it back into another side, and you reduce your energy consumption. That is the carrot. And you also reduce greenhouse gas emissions of the heat load. Okay, so 2 incentives, one that can turn into an economical one, the other one more of an environmental one right now. What are the 3 principles involved in waste heat recovery? Like I said, first you capture the energy available in one process, whether it is through a liquid or gas, that's a source. You transfer this energy to the heat, and you reutilize the energy in the load. So basically you go from the hot side to the cold side, so from the source to the load. So I already, as mentioned before, what are the advantages of doing this is basically reduce your energy consumption and the greenhouse gas emission. And why is this of interest for mining? It's because sectors that are energy intensive are also the place where there's probably the most potential for the implementation of heat recovery projects. Just to give you an idea of what we're talking about, a mine that produces about 8,000 tons per day has a significant energy consumption just at the, let's say, the underground piece. This could be equivalent to 9,000 households in terms of energy consumption. Then all that ore has to be processed on surface. That processing accounts for additional energy that could be equivalent to another 7,000 households. So to produce and process these 8,000 tons per day, you're talking about the equivalent of 16,000 households. That's a significant amount of energy, okay? Which also means there's a significant amount of energy that is being wasted in that process. So what are the steps for integration, the energy recovery? First, you need to identify what are your sources. Then you need to identify what are your loads. Then you need to quantify what can go from the source to the loads. And the last step is to look at when and how can you do that. So how can you recover the energy on the source, which will require some equipment. Let's say in this case, for example, heat exchangers. You'll need to transfer that to the source and then put it into the load, sorry. The problem is that the energy is actually a combination of 2 variables, power and time. So in order for these transfer to happen, you'll have to find the right moment in time where that can happen as well, where you have the power, the requirements, and the source by the same power and then at the same time. We'll talk about that later. So in terms of the sources, we can roughly identify 4 of them. So type 1 is the heat available in processed water of a treatment plant. Type 2 can be the heat available within the exhaust air. Type 3, the heat available within electrical or mechanical rooms. And type 4, which is a specific type of type 3, is heat available in cooling of mechanical system, which is bigger system that require their independent cooling system. Okay. On the load side, once you capture this heat, where can you put it? And basically, you can use it for building heating, or you can use it for ventilation heating requirements, or for water heating. Okay. Just in simple terms, think about preheating. So you take the energy of what you're dumping into the environment, and you use that for preheating the liquid or the gas that is going into another process. That way you can save the energy, basically. So for example, the type 1, we can look at the mill. So the mill will take ore and will take water going in, plus other components, of course. And then there'll be an output going to the thickener, and then to the discharge to the tailings. So from the thickener, there's the amount of water that can be recovered. That water comes at a certain temperature, normally higher than the inlet water. And at that point, if you install, for example, heat exchanger, you can recover that energy from there and make it available to bring it to a load. Okay. For the type 2, the classical example is the exhaust air of the underground mine, where you can have a significant amount of energy available all year round. Okay. The type 3 can be, for example, an electrical room with multiple transformers or variable speed drives, or even the compressor room. And there you can recover the energy, which is basically heat in the air. Okay. Last type 4, which is also heat available within the cooling of mechanical equipment, is the case, for example, when you have generators in let's say a remote mine. The amount of heat that the generators are going to provide is significant for them to have their specific heat exchanger to provide cooling as required. So then you'll have an extra source for heating that you can bring to the loads. On the load side now, basically the first one is your building envelope. So all the heat that is lost by the walls and the roof of your building, you need to replace that. And a way of doing that is bringing the heat from the source and providing it at the inlet of the system for heating the building as a preheating of the air, for example. And then you start bringing down the load as a result and generating the energy savings. The other type 2, which is for example, the fresh air heating. Normally, it's very popular in Ontario to see heaters installed in the fresh air, mainly for the winter and shoulder seasons, where the inlet temperatures usually have to be in the range of 3 degrees or 5 degrees. The surface temperatures at that time of the year will probably vary between -30 to +3, and then you'll need to compensate that difference with burners, right? So at that place, instead of using the burners to full capacity, you can have a heat exchanger, maybe even connected to the same exhaust of the mine, for which there are already solutions developed that CEMI has been showcasing already. And then you can bring the heat from the exhaust to preheat the inlet, and then save a significant amount of energy on the burner side, burner consumption. Type 3. So there's a significant amount of water that needs to be used in mine sites. The example here is the showers, which is not really the most significant one, but it is one. And basically what happened is whatever heat that you capture in other processes, you can either use it for processes that need hot water, like is shown here, or even warming up the air that is needed on the dries, for example. In any case, the amount of energy that can be saved is significant. So we developed a hypothetical case study based on some information that we had available from some previous project that had been developed by CanmetMINING. In particular, Jan had worked with some of the data of Eleanor mine in the past, not too long ago, 2018. And he used that data to develop an estimate between the heat that was available in the source and also in the loads. So if you look on the table on the left side, basically it shows the type of buildings and the ventilation requirements, where of course the biggest one is the underground mine, then the heating power, and also what type of source and load that each one of these items was. And in order to show that even if you have one source, you can have multiple loads where that heat could be applied to. On the left side, we generated a year balance for the thermal sources and loads. So on the top of the table, you have the thermal sources. Of course, these numbers were generated under a certain amount of assumptions, but we generated a total of over 60 million kilowatt hours of energy that was available. And then on the thermal loads, the loads were significantly less for the same annual addition. And if you assume that 50% of that energy that was wasted could be reused, it could generate some significant savings in terms of money, in the orders of $1.2, $1.3 million a year, and also savings in greenhouse gas emissions. However, this year balance is a little bit of a happy picture because, like I said before, the energy has two variables, power and time. So you actually need to give bigger granularity to this analysis to actually properly estimate how much of the energy available at the source through the year will actually be able to be transported into the loads, okay? And that's where the CanmetMINING team is helping right now, as we're developing a simulator that can do that job. So basically, what we're considering right now for that is the following components. So one is the behavior of the thermal source and load according to the operating conditions, which means how much you use them over the year. And for that, we'll consider also the temperature of the source and the loads to see how much can go from one to the other. And also the efficiency of the equipment that is used to generate this heat recovery. With all that together, the idea is to generate this simulator that will be able to integrate all the load and sources of the mine site to estimate what is the best use of the heat recovery during the year, okay? And even maybe there's some applications that are shown at the bottom right there in terms of the organic turbine as an optional to generate hydro as well. And basically the elements that will be considered by this simulator are going to be the geographical position of the site, which is going to give us an input of the temperature profile on surface over the year, the mining operation conditions, as I mentioned previously, equipment performance as well, then the transfer capacities between the source and the loads, and also the temperatures between the source and the loads, which are kind of tied with the capacities. What is that we expect to get out of the simulator? Basically is the energy recovery and the associated savings with that. Same with the greenhouse gas savings that can be produced by the energy recovery that can take place. And some KPIs in terms of the performance of the transfer between source and loads during the year, and operating temperatures as well for both. And depending on the input we get from some suppliers in the heat transfer, it might be some preliminary sizing of the equipment that will be necessary to generate this heat recovery. Finally, as conclusions here, the mining sector consumes a large amount of energy. Thus, it is a very good place to start trying heat recovery technique, waste heat recovery techniques. The incentives to do this are basically the energy consumption that can be reduced, which can be turned into an economic incentive, and also the GHG production. The development of this energy simulator adapted for the mining sector will helpfully stimulate the implementation of these energy recovery practices and projects in the sector. And it is a good example of a sustainable development and to benefit the environment. And that's it. That's a contact information for Jan, myself, and Charles. That's it for me now, Charles.
Thank you, Enrique. Thank you very much for that presentation. We're going to move into the question and answer period now. Enrique, we do have a couple of questions that have been asked, and I'm going to read them out to you, and then you can answer them one at a time. So the first question we have is from Opasana, and the question is, what is the temperature range of waste heat coming out of the mine? And the question specifically is, what is the maximum and the minimum heat that can be captured, within the mining operation?
So the first question about the exhaust of the air, because I have some ventilation background, I know that between the exhaust and the inlet, you can probably look at about 10 degrees difference. And I've seen that through some of the other presentations that you have done with some suppliers that provide that type of technologies as well. So it's kind of in that range. In terms of what can be recovered as a full mine site, that I guess it goes more into the it depends type of answer. And yeah, it will depend on where's the mine site, what size of a mine site and production you have, and what are also the prices for the energy that you pay. It's not the same if you're in a remote location that if you're close to the services, in a city like Sudbury, because your incentives to go after heat recovery will be different, and as such, the paybacks and the size of the projects that you can implement too, right? So yeah, I wouldn't be able to provide a straight answer to that part of the question.
Okay. All right, thank you for that answer, Enrique. And another question here is from Charles, and the question is, what are some current examples of heat capture and reuse? And maybe if I can just jump in, Enrique, on that one is, we are aware of an air-to-air heat exchange system that is being manufactured by a company called Gupex out of Norway. And they take low-grade heat coming out of the ventilation system, and they capture that heat, and that heat is reused to offset the cost of heating air that's going back underground in colder climates. So Enrique, maybe if you can give us some other examples of heat capture and reuse that's happening out there.
Okay, so yeah, the one you gave there is the kind of the ideal case for the ventilation system, where you recover the heat from the exhaust and use it to preheat the inlet of the mine. I'm not aware of such a system installed in Canada yet. Like you said, I'm aware of such systems installed in Sweden by that company you mentioned. What I have seen, I was doing a little bit of a review on the applications here in Canada, and there was a couple of examples, I think, with the company Agnico Eagle, at some of their mine sites. Some of the heat generation was on the diesel generators they had. Diesel generator will usually generate an output of 30% of electricity of the energy they use, and 30% will be lost through the radiator, and the other 30% through the exhaust gases. So there's a couple of projects there, I think, within the same company of how to use that heat, at least the one from the radiator piece, to provide heating for the camp and some of the shops on surfaces. That I've seen that one. And I also seen some providers trying to use the heat from the exhaust of those motors to try to generate electricity as well. But that one, I saw the news, but I couldn't find, they wouldn't advertise exactly where was the site. They just said that they were working on a site. So I'm not exactly sure where that one is.
Okay, excellent. Thank you for that answer, Enrique. Next question here is from one of our guests. And the question is, what is the maximum recovery for an ORC with temperatures well above what you are talking about, say 10 to 40%? And the next part of the question is, where does your 50% estimate come from? And is this super low grade heat?
Okay, so for the first question, I don't have those numbers handy, but I can, if the person that is asking the question can leave me a contact, we can follow up with him later. And the 50% comes from some of the analysis that Jan has done in his previous work, and with some of the estimates that he thinks are reasonable. But again, this is a hypothetical case study based on some conditions he observed at just one mine site, right? And there's a significant number of considerations to that. So just throwing out a number that could be extendable to anything, I'm not too comfortable doing something like that. And again, if the person would like to reach us out after these, we can follow up on that discussion.
Gotcha. And as maybe next question, a follow up to what we're just answering here is I guess maybe the statement really is you have to consider pumping air or water costs as well.
Yes. There's a transfer from the source to the load that you need to consider. So there's CapEx and OpEx involved. So, and there's maintenance too, right? So yeah, there's a number of components. And the other thing that we didn't touch too much on here is that there's an impact of, depending on how far the source and the load are, in terms of how much more expensive the CapEx is going to get because of that, and also in terms of the losses, right? So there's also some distance limitations to these that hopefully will be built to some extent into the simulator as well.
Exactly. Thank you for that. And a question from Sasha here is, do you see any need for thermal energy storage to recover waste heat and allow reuse during demand? Any high temperature waste heat?
That's interesting. I'm not sure how exactly, maybe that's a question for Jan, but right now the objective of the simulator is to use whatever is available at a certain time of the day to be transferred to a load, as opposed to be transferred to a storage. I think the storage component we're not considering right now, but maybe it could be a good idea for the follow-up project after this as a further improvement to this initial step.
Okay, thank you for that answer. The next question is from Charles here, and the question is, are there any applications where waste heat is being used for things like greenhouses, or for growing things like plants, or regreening, and also for growing plants to both capture waste heat and CO2? Is there any thoughts around that?
No, to be honest, right now I'm not sure what is the answer to that question, because the scope of the work that we have been developed is more around the simulation and the transfer from the source to the load.
Gotcha. Okay, thank you very much. Another question that I have here is that's on my private message here is, how much time would it take for you to run the simulator?
So when the simulator is developed, running the simulator is really not going to take that much time. The piece that is going to take the longest is to get quality data from the site to feed it to the simulator. And then your results will come fairly quickly out of that.
Another question we have from Randy is, are you aware of any higher temperature waste heat, something greater than 300 degrees Celsius, other processes throughout the mining vertical, downstream, processing, smelting, etc.?
No, Charles, my experience in mining is mostly into underground mining.
Yeah.
And he's the expert on the surface piece there and the processes. So I would definitely leave that question for him. So if he wants to leave us his contact, I'll be more than happy to generate that link after with Jan.
Exactly. Thank you for that. And then maybe to add on to that answer, we are looking for plants and operations that do have those components of their system where waste heat is being lost. And the idea with this study is to be able to do those calculations and give you the evidence that if you did reuse some of that heat, it would definitely result in some of those other benefits. And I have a question here about the company I mentioned. It's a Norwegian company, and the company's name is Gupex. And I'll just put the name here in this chat box. It's Gupex, Gupex, and you can see that name in the chat box.
Yeah.
I think we've got about 2 minutes to go here before we end our presentation. And maybe we're going to ask Enrique another question is, what is the expected engagement between a company and CanmetMINING in doing the assessment? Like, just maybe give us an idea on what the engagement could look like for the purpose of the simulator.
Well, like I said before, we need the company so we need to get together to define exactly what is the data that we need from the mine site.
Yeah.
Set up a way of getting that data. Either it is them measuring at site and sending to us, or us having to go there, do the measurement, and then load the data into the simulator, and then get the assessment of the energy transfer modeling, so they can have an idea of where is the highest potential for that transfer, and what is the order of magnitude of the savings that they could be looking at. And then they could start triggering all the engineering phases that will be required for making that happen, right?
Okay. And another question I have here is, I knew someone was going to ask this question, is what does it cost to be involved with CanmetMINING on this project?
Maybe, that's interesting. I think that will be on a case by case. It's not like we have a price ticket that I can just go out and share.
Okay.
But initially, I think the first time we're just looking at getting the data, and so being able to use initially, not sure if anything else other than maybe covering for the trip was included, but we'll have to discuss when that person shows up with that company, exactly how the arrangement is going to be.
Gotcha. Yeah, there's another statement here from, I think it's from Michelle to Randy, that there are high-grade waste heat sources from smelting and refining, but most mine sites don't have these located next to the mine. So thank you for that, Michelle. Just clarify that statement. Folks, thank you so much for coming to the webinar. This is the end of our presentation, and I'm going to ask Enrique just to say the final goodbye to everybody. Enrique, please go ahead.
Okay, thank you very much, everyone, for taking the time to attend this presentation. And I hope that this could incentivize you guys to start some of the heat recovery projects soon in your companies.
Thank you. All right. Have a good day, everybody.
Okay.